Welcome all. In this session, we will see the concept of Lenz law and motional EMF. In the previous section or in the previous class, we have seen that whenever magnetic flux linked with the coil changes and EMF induced in it, and induced EMF directly proportional to rate of change of magnetic flux. This concept already was seen by Faraday first law and Faraday second law. Now in this session, we will see what is the direction of induced EMF. Concept is the Lenz law. Lenz law. Right. To understand the concept of Lenz law, again we will take a magnet and a conducting coil. Right? Shall I take? See here, this is nothing but magnet. This is magnet I can take. Say it is north pole and south pole. Now we will take a conducting coil. This is the conducting coil I can take. Say the coil is closed. We know that magnetic field lines. How the magnetic field lines can go for north pole? These are nothing but magnetic field lines of the north pole. Right. This coil contains many circular turns. Shall I take only one circular turn and a magnet? We know that whenever this magnet is moving towards the coil, magnetic flux linked with the coil changes, EMF induced in coil. Due to EMF, current can flow because this coil is closed. Current can flow. Right. Whatever this current induced due to this change in magnetic flux, the induced current opposes the change in magnetic flux, or the induced EMF helps to grow the change in magnetic flux. The induced EMF either decrease the magnetic flux or induced current increase the magnetic flux. How it decrease, how it increase, that we will see. Before that, this coil contains many circular turns. Many circular turns here. We know that according to Faraday's second law, what you can take? EMF induced directly proportional to rate of change of magnetic flux along with minus sign. What is minus sign here? Direction of induced EMF opposes the change in magnetic flux. See here. Now initially I will write the statement, then we will go further how Lenz law can be understood. See here. Lenz law statement says that the direction of induced EMF direction of induced EMF always such that opposes cause producing it. What is meaning of this? Direction of induced EMF always such that opposes cause produce it. Very simple. By what cause this EMF induced? By what cause this current induced? This current induced by moving the magnet, by changing magnetic flux. Simply Lenz law says that the induced current or induced EMF opposes the change in magnetic flux. This current comes due to change in magnetic flux, and induced current that opposes the motion of the magnet. What is cause here? Cause mean either motion of the magnet or by changing in magnetic flux, EMF induced. That is the cause. That to that cause the EMF induced can oppose. That is the Lenz law. How it opposes, that we will see in detail now. Now, this coil contains many circular turns. Shall I take the bar magnet and only one circular turn? I can take only one circular turn. Look at me. It is a magnet. This is the north pole. This second called south pole. So simply I can take a circular coil. This is circular coil. Right. We know that these are nothing but magnetic field lines. These are the magnetic field lines. When bar magnet is moving towards the coil, bar magnet is moving towards the coil, how the current can flow? Current can flow in anti-clockwise direction. Current can flow in anti-clockwise direction. Wherever current can flow in this coil, current carrying coil produces its own magnetic field. Own magnetic field means this current carrying loop is act as a magnet, because we know that in the last chapter we have learned that a current carrying loop act as a magnet. If current can flow in anti-clockwise direction, then how it is acting? One end act as a north and second one act as a south. This end act as a north. Later on, when current can flow in anti-clockwise direction, this gives the direction of the current. And this end act as a north, this end act as a south. Are you following? When bar magnet is moving, induced EMF creates its own magnetic field. Due to that magnetic field, one end act as a north, second one act as a south. Then north and north repel each other. How it opposes? It opposes due to creation of the magnetic field. By creating the magnetic field, it acts as magnet, and magnet one end acts as a north, second one acts as a south. North and north repel each other. When bar magnet is moving towards the coil, this coil repel the magnet. That is the oppose. That is nothing but oppose. Now second case we will take. How second case we will take? Same coil will take, but north pole is moving away from the magnet. Look at here. Again I can take it is a magnet. Say I can call this a north pole. Now this is nothing but coil. Are you following this? And for this, how the magnetic field lines are there? These are nothing but magnetic field lines, because it is north pole and magnetic field lines must be going like this. These are magnetic field lines. This magnetic field, both are opposite in direction. Due to opposite in direction, they can repel. Now, these are nothing but magnetic field lines of the given bar magnet. Now, this bar magnet moving away from the coil. Wherever bar magnet is moving away from the coil, current can flow in clockwise direction. Wherever current can flow in clockwise direction, then it acts as a south and north pole. How it is act as south and north pole? This is act as a south pole. Then what about this pole? This act as a north pole. Then due to this current loop, how the magnetic field lines can there? These are nothing but magnetic field lines. This is north pole. These are magnetic field lines. Later on, when north pole of the bar magnet moving away from the coil, there also EMF induced. The induced EMF or induced current opposes the magnet by attracting. In this case, attracting takes place. In this case, repelling takes place. So that direction of induced EMF always opposes cause produces it. By what cause it produces? It produces by motion of the magnet. To that motion, the EMF induced can oppose. That is nothing but Lenz law. Right. But the Lenz law says that there is conservation of energy. How it conservation of energy? Wherever bar magnet is there, initially bar magnet is moving. Bar magnet moving means mechanical energy applied. Wherever mechanical energy applied, magnetic flux changes. Wherever magnetic flux changes, what it changes? Magnetic energy changes. Due to change in magnetic flux, what is produced? Current produced, so that electric energy produced. Here three energy takes place. Mechanical energy applied, then magnetic energy changes. Wherever magnetic energy changes, electric energy produced. Energy not be created, energy not be destroyed, simply it convert from one form to another form. Initially mechanical energy applied, magnetic energy changes. Due to change in magnetic energy, electric energy is produced. So Lenz law indicates there is conservation of energy. Significance is conservation of energy. Right. Later we will go motional EMF. Next concept we will go. Next concept is the motional EMF. In detail we will see. See here. motional EMF. Look at next concept is motional EMF. Meaning is, in a uniform magnetic field or non-uniform magnetic field, if a conductor moves, in that conductor EMF produces. That EMF we are calling motional EMF. We'll explain in detail. Now, to explain the motional EMF, I will take a uniform magnetic field. That magnetic field is uniform and directed into the plane. How it is? This is nothing but uniform magnetic field. This uniform magnetic field is uniform and directed into plane. Magnetic field is uniform and this magnetic field is directed into the plane. Remember, this is nothing but uniform magnetic field lines, right? That is uniform magnetic field lines. Now, in this uniform magnetic field, how it is? Direction must be like this. In this uniform magnetic field, now I can take a rectangular loop. In this rectangular loop, one of the side is free to move. Let us take, I can take one side. Say this is nothing but rectangular loop. I can name it as ABCD. It is nothing but ABCD is nothing but rectangular loop. In this rectangular loop, the side BC is free to move. The side BC is free to move. When the side BC is moving in uniform magnetic field, EMF induced. Due to EMF induced, that EMF we are calling motional EMF. How it is? Look at me. When this conductor moving it in magnetic field by velocity V, in this conductor, when this conductor moving in magnetic field, in this conductor induced current and induced EMF also produced, that we are calling motional EMF. Current also produced and EMF also produced. How it is produced? We know that magnetic flux. What is magnetic flux? Magnetic flux is nothing but scalar product of magnetic field and area vector. How magnetic flux changes? Either by changing in magnetic field, magnetic flux changes. By changing in area vector, magnetic flux changes. Either by changing in angle between area vector and magnetic field, magnetic flux changes. Wherever magnetic flux changes, EMF also induced according to Faraday's second law. Right? Here what happens? Wherever this conductor moving in magnetic field, what it changes? Area changes. Wherever area changes, EMF induced. That we are calling motional EMF. How to define motional EMF? The EMF induced in conductor. EMF induced in conductor. EMF induced in conductor. EMF induced in conductor by moving it in magnetic field. By moving it in magnetic field. Moving it in magnetic field is called as motional EMF. Is called as motional EMF. Now let us see how the motional EMF, how the induced current and how much power generated in the conductor, that we'll see in detail. See here. Later we will see how the direction of the motion of the conductor and what is the direction of induced EMF, that also I will explain. Initially we know that magnetic flux. See here. What is magnetic flux? Magnetic flux is equal to scalar product of magnetic field and area vector. In this case, what is the direction of magnetic field? This is the direction of magnetic field. I can take this conductor free to move in uniform magnetic field. This conductor, how much length is available? L is the length. Right? L is the length of the conductor. When this conductor moving it in magnetic field by velocity B, by what distance? By x distance. Now this length and this one looks like a area loop. So for this area, how to write? Area is equal to how much? Magnetic field, keep it up same. So length into breadth, that becomes area. This is called as equation number 1. Whenever this area change, wherever area change, magnetic flux changes. Because when this conductor moving like this, area changes. Wherever area change, magnetic flux changes. Wherever magnetic flux changes, according to Faraday's second law, EMF also produces. According to Faraday's second law, what was the definition? Magnitude of induced EMF directly proportional to rate of change of magnetic flux. So I can call this the equation 2. This is the equation number 2. So put equation 1 into what we will get? E is equal to d by dt, keep it up same. What is phi? Phi is equal to B L into x. Here what is constant? Magnetic field is constant, length is constant, x is variable. Then E is equal to B into L, keep it up same. Dx divided by dt. Dx by dt is nothing but velocity. Dx mean displacement, dt mean time. E is equal to how much then? E is equal to B L into phi. This is induced EMF. Right? Whenever conductor moving it in magnetic field, EMF can induce. Wherever EMF induced, this circuit is closed, then current also induced. Consider the side BC has resistance. So remaining all sides are negligible resistance in this case. Remember, we know that according to Ohm's law, E is equal to I into R. What is E? Induced EMF. I induced current, R represent resistance of the conductor. Or what is induced current in this case? Induced current I is equal to how much? I is equal to E divided by R. E is this value. I is equal to BLV whole divided by R. This I can call induced current. Right? How the current can flow in this case? Current can flow in this case. My question is, when conductor moving, mechanical energy applied, mechanical power applied, all the power, mechanical power applied can be generated as a electric power. How it is? When a current carrying conductor, this is a current carrying conductor placed in magnetic field, it experiences magnetic force. This concept you have seen in last chapter, moving charges and magnetism. When a current carrying conductor of length L of current carrying I placed in magnetic field B experience magnetic force. How much magnetic force? F is equal to BIL. Right? If the conductor moving, mechanical power applied, all mechanical power dissipated as electric power I am saying. How it is? See here. Force is equal to this value. Then what is power? Power is equal to what value? Force into velocity. Force into velocity. See here, what is force here? Force is equal to BIL. But I is equal to this value. P is equal to, F is equal to what value again? BIL into V. I this value I can take. Then what is mechanical power? This mechanical power P is equal to, B keep it up same. I this value. What about this? BLV. Whole divided by what value? R. Into how much? Into that is V. Right or wrong? Because BLV I am taking BLV. Then what about this power? Power is equal to what value? V square. So V square into L whole divided by R. This is nothing but mechanical power. All the mechanical power generated as an electric power. How it is? See here. We know that power, electric when current is generated, what is power? Power is equal to I square into R. I this value. Then power, I mean I square mean B square, L square, V square into R whole divided by how much? R square, 1R get cancelled. What is power then? Power P is equal to how much? B square, L square, V square whole divided by R value. That is electric power. This electric power must be equal to mechanical power. When a conductor moving in magnetic field, in that conductor EMF induced. That phenomena we are calling motional EMF. This I can take induced EMF, I can call this induced current. I induce nothing but power generated in the conductor. But we forgot to say what is the direction of the motion of the conductor and direction of the magnetic field. Direction of motion of the conductor, direction of magnetic field and direction of induced EMF. How it is? When a uniform magnetic field is there, in that uniform magnetic field, if a conductor moving, in that EMF induced. Direction of induced EMF, motion of the conductor and magnetic field is given by Fleming's right hand rule. What is meaning of Fleming's right hand rule? That will explain in detail. Look at here. Remember. So this I can call induced EMF only. See here. How it is? Very simple. Concept is Fleming's right hand rule. Fleming's right hand rule. Right. Actually, this rule says that if a conductor moving in uniform magnetic field if a conductor moving in uniform magnetic field, EMF induced. Direction of induced EMF, direction of magnetic field and direction of motion of the conductor is given by Fleming's right hand rule. See here. Now I can take this is nothing but uniform magnetic field lines. This magnetic field directed into the plane. Got in my point. Now in this uniform magnetic field, now I can take a rectangular loop. In this rectangular loop, one side is free to move. Let us take only this side is free to move. BC side is free to move. When this conductor moving in this direction, current can flow in anti-clockwise direction. I showed there. Right. Direction of motion of the conductor, induced current and magnetic field is given by Fleming's right hand rule. How it is? 3 fingers of right hand, thumb, forefinger, middle finger are in such a way that they are mutually perpendicular to each other. Are you following? All are mutually perpendicular to each other. Then if I hold like this, in what way conductor moving? In this way conductor moving. In this direction magnetic field is there and in this direction current can induce like this. 3 fingers of right hand like thumb, forefinger, middle finger are in such a way that they are mutually perpendicular to each other. Then thumb indicates direction of motion of the conductor, forefinger indicates direction of magnetic field and middle finger indicates direction of induced current. Like this. How conductor moving? Conductor moving like this. Thumb indicates direction of motion of the conductor, forefinger indicate direction of magnetic field and middle finger indicate direction of induced current. Now situation like this. I won't take like this. Look at me. I can take this nothing but conductor in this uniform magnetic field. Now in this case I won't move conductor inward. Instead I want to move this conductor in outward direction. When your conductor moving in outward direction, how the current can flow in this case? Current can flow in clockwise direction. Look at me here. Direction of the current. How the direction of the current, motion of the conductor and magnetic field is given? 3 fingers of right hand, thumb, forefinger, middle finger are in such a way that they are mutually perpendicular to each other. Look at me. Mutually perpendicular to each other. In this direction conductor moving, thumb indicate direction of motion of the conductor, forefinger indicate direction of magnetic field, middle finger indicate direction of current. Look at me, this is the direction of the current, this is the direction of magnetic field, this is the motion of the conductor. So this is Fleming's right hand rule. I mean, when a conductor moving in magnetic field, we can give the direction of magnetic field, motion of the conductor and induced current and the concept of motional EMF. Right? Remaining concept we will see in the next class. Thank you, students.